Welcome everyone. So we will be discussing Indian contribution to science. This is a book which is compiled by Vigyan Bharati, and this is one of the chapters which is there for the VVM examination. Chapter 6, Mathematics in India. And early astronomers tried to quantify the paths of the sun, the moon, planets, and the stars on the celestial sphere with ever more accuracy, or to predict the occurrence of eclipses. They were naturally led to develop mathematical tools. Astronomy and mathematics were thus initially regarded as inseparable, the latter being the maidservant of the former. Indeed, about 1400 BC, the Vedanga Jyotisha, the first extant Indian text of astronomy, states that two different versions, like the crest of the head of the peacock, like the gem on the hood of the cobra. Jyotisha, astronomy, or Ganita, mathematics, is the crown of the Vedanga Sastras, text on various branches of knowledge. In fact, Jyotisha initially referred to astronomy and mathematics combined. Only later did it come to mean astronomy alone. India's first urban development, the Indus and Harappan civilization in 2600 to 900 BC, involved a high degree of town planning. A mere glance at the plan of Mohenjo-daro Acropolis or Upper City, Dholavira, the run of Kutch, the Kalibagan, that is in Rajasthan, reveals the fortification and streets generally aligned to the cardinal directions and exhibiting right angles. Specific portions in the dimensions of major structures have also been pointed out. All this implies a sound knowledge of basic geometrical principles and an ability to measure angles, which, with the discovery of few cylindrical compasses made of shell with slits cut every 45 degree, has confirmed. Besides a trading purpose, the Harappan developed a standardized system of weights in which initially each weight was double the preceding one, then 10, 100, or 1000 times the value of the smaller weight. This shows that the Harappans could not only multiply a quantity by such factor but also had an inclination for the decimal system of multiples. However, there is no agreement among scholars regarding the numeral systems used by Harappans. There is so no scholarly consensus of the dates of the four Vedas, India's most ancient texts, except that they are over 3000 years old at the very least. We find in them frequent mentions of the numbers by name, in particular multiples of tens, hundreds, and thousands, all the way to a millions and millions in the Yajurveda. A number called Paradha. By comparison, much later the Greeks named the numbers only by up to 10,000, which was a myriad, and only in the 13th century CE would the concept of million be adopted in Europe. The Brahmanas' commentaries on the Vedas knew the four arithmetical operations as well as basic fractions. Early historical periods, the first Indian texts dealing explicitly with mathematics are the Sulba Sutras, dated between 8th and 9th century BC. There, they were written in Sanskrit and in the highly concise sutra style, and were in effect manuals for the construction of fire altars called siddhis or vedis, intended for specific rituals and made of bricks. The altars often had 5 layers of 200 bricks each, the lowest layer symbolizing the earth and the highest the heaven. They were thus symbolic representation of the universe. Because of their total area needed to be fully defined to constructed from bricks of specialized shapes and sizes, complex geometrical calculation followed. Sulba Sutra, for instance, our earliest text on geometry offering a general statement in geometric form, and so called Pythagoras theorem, which was in fact formulated by Euclid around 300 BC. They spelled out elaborate geometric methods to construct a square resulting from the addition or subtraction of two other squares or having the same area as given circle, the vice versa. The classical problem of squaring of a circle or circling of a square, which because of pi transcendental nature cannot have exact geometrical solutions, only approximate ones. All these procedures were purely geometrical but led to interesting corollaries. For instance, root 2 was given a rational approximation which is correct to the fifth decimal. The Sulba Sutra also introduced a system of linear units, most of them based on dimensions of human body. They were later slightly modified and became the traditional unit used across India. The chief unit were 14 annas, grain of common millet is angula, a digit, 12 angulas, 1 pradesha, that is span of hand, later vitasti, 15 angulas, 1 pada or big foot, 24 angulas, 1 aratni or cubit, later hasta, 30 angulas, 1 prakrama or step, 120 angulas is equal to 1 purusa or height of a man with arms extended over his head. A few centuries later, Pingala Chandrasutra, a text on Sanskrit prosody, made use of binary system to classify the meters of Vedic hymns, whose syllables may be either light, which is Lagu, or heavy, which is Guru. Rules of calculation were worked out to relate all the possible combinations of light and heavy syllables expressed in the binary notation to numbers in one-to-one relationships, which of course worked both ways. In the course of those calculations, Pingala referred to the symbol for Sunya or zero. About the same time, Jaina texts indulged in cosmological speculation involving colossal numbers and dealt with geometry combinations and permutations, fractions, square, and cube powers. They were first in India to come up with the notation of an unknown, that is Yavat Tavat, and introduced a value of pi equal to root over 10, which remained popular in India for quite few centuries. With the appearance of Brahmi script a few centuries BCE, we came across India's first numeral on Ashoka's edicts in particular, but as yet without any decimal positional value. The numbers were evolved in shape, eventually bought by Arab scholars. They will be transmitted and with further alterations to Europe and become our modern Arabic numerals. The classical period, if we talk about, together with astronomy, Indian mathematics saw its golden age during India's classical period, beginning more or less with the Gupta's age, that is from about 400 CE. Shortly before that period, the full-fledged place value system of numeral notation, our modern way of noting numbers, unlike non-positional system such as those depicted above or Roman numbers, had been worked out integrating 0 with the 9 numerals. It's a pity that we shall never know who conceived of it. Amongst the earliest known references to it is a 1st century CE work by Buddhist philosopher Vasumitra, and it is worked out more explicitly in the Jain cosmology work Loka Vibhaga, written in 458 CE. Soon it was adapted across India and later taken to Europe by the Arabs. This was the major landmark in the world's history of science since it permitted rapid development in mathematics. About 499 CE, living near what is today Patna, Aryabhatta I, born in 476 CE, authored the Aryabhatiya, the first extant Siddhanta, attempting a systematic review of the knowledge of mathematics and astronomy prevailing in his days. The text is so concise, just 121 verses, as to be often obscure, but between the 6th and the 16th century, no fewer than 12 major commentators were authored to explicate and build upon its content. It was eventually translated into Arabic about 800 C under the title Ziz al Arjabhar, which in turn led to a Latin translation in 13th century in which Aryabhatta was called Arduvarius. The mathematical content of Aryabhatiya ranges from a very precise table of sines and an equal precise value of pi to be 3.1416, stated to be approximate to the area of a triangle, that sums of infinite arithmetic progression, algorithms for the extractions of squares and cube roots, and an elaborate algorithm called Kutaka, which is pulverizing, to solve intermediate equations of the first degree with two unknowns, ax plus c is equal to by. By intermediate is meant that the solution should be an integer alone, which rule out the direct algebraic method. Such equations came up in astronomical problems, for example, to calculate a whole number of revolutions of planet in a given number of years. It is worth mentioning that despite its great contribution in Aryabhatiya is not free of errors. Its formula or volumes of pyramid and spheres were erroneous and would be later corrected by Brahmagupta and Bhaskaracharya respectively. The classical period, that is post Aryabhatta, born in 598 CE, Brahmagupta was an imposing figure with considerable achievements in mathematics. In Brahmashubhuta Siddhanta, he studied cyclic quadrilaterals, that is inscribed in a circle, and supplied the formula for their area, a formula rediscovered in 17th century Europe. If ABCD has sides of length ABCD and semi perimeter is S equal to A plus B plus C plus D divided by 2, then the area is given by ABCD is equal to root over S minus A into S minus B into S minus C into S minus A. S minus D. Brahmagupta boldly introduced the notion of negative numbers and ventured to define the mathematical infinite as Kacheda, or that which is divided by Kha, Kha being one of the many names for zero. He discovered the Bhavana algorithm for integral solutions to second order intermediate equations called Varga Prakriti of the type nx square plus 1 is equal to y square. He was in many ways one of the founders of modern algebra, and his works were translated into Persian and later Latin. Dated around the 7th century, the Bhakshili manuscript named after the village now in northern Pakistan, where it was found in 1881 in the form of 70 leaves of bark, gives us a rare insight into the extensive mathematical calculation techniques of the times, involving the particular fractions, progressions, measures of time, weight, and money. Other brilliant mathematicians of Siddhantic era included Bhaskara I, a contemporary of Brahmagupta who did pioneering work in trigonometry. Sridhara and Mahavira, the last a Jain scholar who lived in 9th century in the court of Rashtrakuta king in today's Karnataka, authored the first work of mathematics that was not as a part of a text on astronomy. It is Mahavira dealt with finite series expansion of fractions, permutations and combinations, linear equations with two unknowns, quadratic equations, and a remarkably close approximation for the circumference of an eclipse, among other important results. Graph showing the high accuracy of Bhaskara one's rational approximation for the sine function from 0 degree to 180 degree in blue. The sine function had to be shifted upward by 0.05 to make the two curves distinguishable. Bhaskara II, often known as Bhaskaracharya, lived in the 12th century. His Siddhanta Shiromani, literally the crest of jewel on of the Siddhantas, broke new ground as regards cubic and biquadratic equations. He built upon Brahmagupta's work on intermediate equation to produce a still more effective algorithm, the Chakrawala, a cyclic method. With it, he showed, for instance, that the smallest integral solution to 61x square plus 1 is equal to y square, and x is equal to 226153980 and y is equal to 17663199049. Interestingly, 5 centuries later, the French mathematician Fermat offered the same equation as a challenge to some of his contemporaries. Bhaskaracharya also grabs the notion of integration as a limit of finite sums by slicing a sphere into ever smaller rings. For instance, he was able to calculate the area and the volume. He came close to the modern notion of derivative by discussing the notion of instant speed, Tatkalika Ghati, and understood that the derivative of the sine function is proportional to the cosine. The first part of Bhaskaracharya's Siddhanta Shiromani is collecting of mathematical problems called Leelavati, named after a unknown lady to whom Bhaskaras put problems in an often poetic language. Leelavati became so popular with students of mathematics across India that 4 centuries later Akbar had it translated into Persian by a court poet. The Kerala School of Mathematics. Along with the astronomy, mathematics underwent a revival in Kerala school, which flourished there from 14th to 17th century. As pioneer, Madhava laid some of the foundations of calculus by working out power series expansions for sine and cosine functions and by spelling out this fundamental expansion of pi. This is known as Gregory Leibniz series, but out one day to be named after Madhava. He went out to the propose a more rapidly convergent series of pi, which enabled him to calculate pi to 11 correct decimals. Neelakantha Somyaji and Jeshtadeva built on such results and considerably enriched what might be called the Indian foundation of calculus. The latter, for instance, worked out on binomial expansions. As elsewhere, mathematics in India arose from practical needs, constructing fire altars according to which precise specification tracking the motion of planets, predicting the eclipses, etc. But India's approach remained essentially pragmatic rather than developing an axiomatic method such as that of Greek. It focused on obtaining formulas and algorithms that yielded precise and reliable results. Nevertheless, Indian mathematicians did often provide logical, rigorous justification for their results, especially in longer texts. Indian Bhaskaracharya states that presenting proof is part of the teaching tradition, and Jeshtadeva devotes considerable space to them in his Yukti Bhasha. The shorter text, on other hand, often dispense with the development of the proofs. In the same spirit, the celebrated S. Ramanuja produces many important theorems but did not take time to supply proofs for them, leaving this for others to do. Whether those specificities limited the further growth of Indian mathematics in the open to debate. Other factors have been discussed by historians of science, such as historical disruptions of centers and networks of learning, especially in the North India, limited to royal patronage or absence of conquering impulse, which is Europe did fuel the growth of science and technology. Be that as it may, India's contribution in the field was enormous by any standard. Through the Arabs, many Indian inputs from the decimal place value systems of numeral notions to some of the foundations of algebra and analysis traveled on to Europe and provided crucial ingredients to developing of modern mathematics. Thank you.